Okay, this is a solution to structures number 4. This is the one that looks like this. You have, on the left side, you have a pin joint on a wall and a straight member like that, and then it's connected to a semicircular member which is connected to a pin joint at the ground. These are connected by a pin joint. The diameter of this circle is 0.6, so the radius of that circle is 0.3 meters. It has a mass of 50 kilograms. The straight member has a length of 0.4 meters. And this angle is 30 degrees. Okay, and we want the external loads on each member. Well, the first thing to do with structures problems is to number the members, and I'm going to also label the joints. So I'm going to call this member 1 and this one member 2. Of course, you could do this problem with the opposite numbering too. And in the end, the answers will be the same, but some of the steps in the middle will look different. And I'm going to label the joints. I'll call this A, B, and C. And really, the reason I'm doing that is because to clear up what's happening at some of these joints, it helps to draw those side pictures of the joints. And so I'm going to do that, and I'll label them with the joint numbers. One thing we're going to have to use is the formula for the centroid of a semicircular arc. And I'll show you what that is. There's a link. I guess it's not a link. It's a, but it tells you how to find that centroid formula. Okay, well, let me start by drawing side profiles of each of the joints so you can see what happens at each one of these joints. So at joint A, that's the one at the wall, and imagine I'm gonna draw this from like the, looking from the left side to the right side. So what you would see is, you would see the ground. Okay, so this is G. And then you would see a pin joint that goes through the bracket connected to the ground. And that pin is part of member 1. Okay. So if you can picture what I'm drawing here, this is really the key to understanding where you apply these forces. So when I draw the free body diagram of member 1, there's going to be a force vector that's applied to 1 by the ground. Okay. And now I'm going to go to joint B. So what do we see if we're looking again from the left side to the right side? So we're going to have a side view of this joint. We have member 1 here. And then member 2 here. Okay. So this is member 1 and this is member 2. But remember that the pin is part of the lowest numbered member at that joint. So the pin is, we're going to treat it like it's part of member 1. It doesn't matter that it's not physically part of it. We can lump those two together and treat them like a single body. So we're not, I mean, this is a totally reasonable thing to do. And so what we see here, okay, so we have member 1 and we have member 2. And then, oh, I left in this picture of the problem, I left off that 1,000 Newton force. Okay, so there's the 1,000 Newton force that drives all this. So, okay, there's also that 1,000 Newton force that's applied to this pin. Well, it would be, from the view that we're taking, it would be going into the page. I'm going to draw it in a different direction. That's not really important right now. What is important is that it's applied to that pin. And since we're treating that pin like it's part of member 1, that 1,000 Newton force is applied to member 1 and it's not applied to member 2. So if I go through these and highlight all the things that are happening to member, I'm going to highlight member 1 in both of these. Okay, you can see that the only thing touching member 1 at joint A is the ground. And what's touching member 1 at joint B is member 2 and also that 1,000 Newton force. And that tells you what's going to appear in those free body diagrams. So now let's go to C. And again, I'm going to draw it from the left side to the right side. So there's the ground. And then there's the pin joint. And that pin joint we're treating as part of member 2. Okay, and so from that you can see that the only thing touching, I'll highlight member 2 in this one in green. So you can see that the only thing touching the boundary of member 2 is the ground. Okay, so now I'm going to draw a free body diagram of member 1, and I'm going to use these side views to be sure that I get this all right. So free body diagram of member 1. Now I'm going back to the usual view. All right, so down here at the lower left end, that is joint A. So what's going on at joint A? What's going on to what's happening to member 1 at joint A? The only thing is a pin joint connection to the ground. And so here we have this reaction force. You could write this as the force on 1 by the ground, or for reaction forces with the ground, a lot of times we don't use the subscripts because we never need to flip them. So you could just call this RA. At the center of this beam, we know that it has a mass of 10 kilograms, so there's a weight force of 98.1. And now go up to the upper right, that's joint B. Okay, so what's going on at joint B on member 1? There's a pin joint connection to member 2. So I'm going to call this the force on 1 by 2. And there's also the 1,000 Newton force. So I'm going to apply that here. And now I'm going to write out the row vector, the force vector, and the moment vector. For an about point, I'm going to use A, I suppose. So for RA, row vector is 0, force vector is RAX, RAY, moment Z component is 0. Then there's the weight force. The row vector for that is 0.2 times cosine and sine of 30 degrees. So that is 1.732, no, 0.1732. And 0.1. Whoops, I put that in the wrong spot. Stupid. Okay, row vector, 0.1732.1. And now the force vector is 0, negative 98.1. Take that cross product. And you get 16.99 negative. And now we can go up to that force F12. The row vector there is twice this row vector. Hold on a second. So that's 0.3464. And 0.2. And the force vector is F12 X and Y components. And so you get 0.3464 F12Y, and then minus 0.2 F12X. And it sort of looks like these are components, but it's not. That's just, I just ran out of room, so I just scrolled down. So that's all just one scalar value. And now Newton's second law says RAX, that's not an X, RAX, RAY plus 0, negative 98.1 plus F12X, F12Y is equal to zeros. So that gives us our first two equations. And I'll write it as RAX plus F12X is equal to 0. And RAY plus F12Y is equal to 98.1. There's equation 1 and equation 2. And now the moment equation. We have negative 16.99 plus 0.3464 F12Y minus 0.2 F12X is equal to 0. And so that gives us our third equation. I'm going to rearrange this. So we have negative 0.2 F12X plus 0.3464 F12Y is equal to 16.99. And that's our third equation. Can we solve this? No, because we have 4 variables and only 3 equations, so we got to keep rolling. So now we'll do a free body diagram of body 2. Let's see what that gives us. Okay, so what's happening to body 2 at the top? That's the joint B, the way I have it here. I named that B. So let's go to the side view of B and see what's happening to member 2, what loads are being applied. Well, member 2 is in contact with member 1 because that pin is member 1. So there is a force F21, and it's a force vector because it's a pin joint. But that 1000 is not applied to member 2. It's applied to the pin, which is member 1. So the only thing we have happening to member 2 is the force on 2 by 1. And since we've already named something F12, I'm going to call this negative F12. You can always do that with Newton's third law. And now we have the weight force, and it's going to act here somewhere. The mass of this thing is 50 kilograms, so this is 490.5. And the distance from the line between the two joints and the centroid comes from the centroid formula. It's 2 times the radius over pi. The radius is 0.3. So that distance is 2 times 0.3 divided by pi. So 0.191. Okay. You shouldn't draw that on the free body diagram. So, but anyways, we're going to use that as a in our calculations for the moments. And now we go down to the last force, and that's what's happening to member 2 at the joint C. So let's go up to the side view of joint C and see what's happening to member 2. And the only thing touching member 2 there is the ground. That's, I'm just going to call that RC, or you could call it force on 2 by the ground. So we have this vector, RC. Okay. And I'll write out the table. What do we want to choose as our about point? I'll choose C as the about point. So I'll first do RC. That's at the about point. So rho is 0. The force is RCX, RCY. Cross product is 0. Then the weight force. You can move the weight anywhere along its line of action. So I'm going to imagine moving that down so it's just horizontally across from the point C. Then the only thing that matters here is to get from the about point to where the force is applied is that distance positive 0.191. And then this won't matter. You could put in anything for that. It doesn't matter. I guess actually let me put in the 0.3. You'll see why it doesn't matter. But and then the force vector is 0, negative 490.5. Now that cross product, you can see that you're multiplying the 0.3 times the 0. That's why it's always okay to move something along its line of action. And you get a cross product of negative 93.69. And then last is the reaction. No, we already did the reaction. The last one is F is negative F12. The row vector, it's just 2 radii up, so that's going to be 0.6. The force is negative F12x, negative F12y. Cross product is 0 times negative F12y minus 0.6 times negative F12x. So that's positive 0.6 F12x. And I'll start with Newton's second law. So Newton's second law says, well, I'm going to do this in my head, but you just add those up, set them to 0. So we have negative F12x plus RCx is equal to 0. That is our equation. Well, hold on a sec. And then sum up the y's. Negative F12y plus RCy is equal to, move the negative 490.5 to the other side, that's equal to positive 490.5. So these are equations 4 and 5. And now the moment equation says 0.6 F12x is equal to positive 93.69. That's our equation 6. For variables, we have the vector RA, the vector F12, and the vector RC. So 6 variables, 6 equations, and we can solve it. I am going to make that table that you use reduced row echelon form with, but through the magic of time-lapse cinematography, it will not appear to take any time at all. Snap. Okay. So there's my augmented matrix. Yours might look different if you did it in a different order of variables, but here's mine in the order that I did. And what you get if you use reduced row echelon form on this is that RA is negative 156, negative 41. F12 is 156, 139. RC is 156, 629. And now to calculate the external loads on each member, just go up to the free body diagrams you did before and put these in. If there's more than one force acting at a point, you can add those vectors up. And for member 2, where you have the negative F12, put in the force vector negative 156, negative 139. And that gives you your external loads on each member. Okay, so that is number 4.